Hey everybody, welcome back. We're going to finish up chapter 3 with differential equations. Differential equations are equations that have derivatives already built into them. And you can imagine there's a physics problem where velocity, which is the derivative of position function, is already embedded inside of an equation. And the goal is to find the function y that is some sort of function of x or t, depending on what we're trying to do. I want to take us back to algebra. And if we were to solve this equation, we would find that x equals 3. And the way we would check that answer is we would plug that into the original problem to verify that the left side equals the right side. That's where we're going to start with our first example. Is we're going to be given a solution. We don't know where it came from, but we're going to be given a solution. And we want to figure out, does it make the left side equal the right side? So let's start here. Now I'm going to notice, by the way, our differential equation of interest is here, meaning it's our equation that already has a derivative. In fact, in this case, it has a second derivative. And we are saying we think that this is a solution. This is an answer to this differential equation. So what I'm going to do is I'm going to find the second derivative. Y prime is 2x, and y double prime is just 2. And I'm going to plug that into here. 2 plus, now y is the x squared plus 5. That's the pink that you see on the left there. Right side is x squared plus 7. And x squared plus 7 is going to equal x squared plus 7. And that is going to check. Meaning, so y equals x squared plus 5 is a solution to y double prime plus y equals x squared plus 7. All right, we are now going to figure out how do we solve these differential equations. Well, you would imagine there are dozens of ways that I've learned in various classes on how to solve lots of different types of differential equations. We are going to stick with what are called separable differential equations. Those are equations that fall into the category where I can separate out the x's and the y's. That includes the dx and the dy, where we end up where the dx and the f of x are on one side of the equation, and the function of y, dy, on the other side. And in essence, we are separating the two variables. A couple of rules I want to keep in mind. So if I have e to the ln of x, that's just x. Also, e to the x plus y is e to the x times e to the y. We're going to keep that in mind, and let's get to our first differential equation. So we have dy dx equals 72yx to the 8th power. We are also given what's called an initial condition. It says the y-intercept, meaning when x equals 0, y equals 5. And that's going to help us with our constant of integration because we're going to have to integrate as part of this. But I'm going to go back to my original, the dy dx equals 72yx to the 8th. I'm going to divide both sides by y and multiply the dx to the other side. So now I have all my y's on one side and my x's on the other side. That includes the infinitesimal, the dy and the dx separated out. I'm now going to integrate both sides. And we can see that I have a plus c as a part of this. I'm going to change this from logarithmic into exponential form. 72 over 9 is 8. And this becomes e to the c times e to the 8x to the 9th. I'm using that rule on the top right corner there, where I'm breaking it up into two separate ones. And I'm going to rewrite e to the c, which is just a constant raised to a constant. I'm just going to rewrite that as an a. And we don't know if a is positive or negative. So what I'm going to do is I'm just going to write it as an equation, and I'm going to plug in my initial condition. By the way, I'm not going to be doing problem 2 here. So I'm going to use the space there. So when y equals 5, a equals 8, 0 to the 9th power. That's just a e to the 0. And e to the 0, of course, is just 1. So this means a equals 5. So my differential equation is going to be 5 e to the 8x to the 9th power. And that is my solution to the differential equation, and it satisfies the initial condition, meaning when x equals 0, y equals 5. All right, let's try a few more. I'm a little out of room, so I'm going to take number 3 and I'm going to move it to a blank sheet. And so we are going to have dy dx equals negative 6y. And we have an initial condition. They specifically say that y of 0 equals negative 6. And this means at x equals 0, y equals negative 6, just to be explicit on what we mean by that. I'm going to divide both sides by y again and multiply the dx to the other side. Then I'm going to integrate. So I've separated the variables. So I'm going to integrate. I'm now going to rewrite this. And e to the c, once again, I'm just going to call a. And based on my initial condition, we'll figure out if it's the positive version or the negative version. Because y is negative, it's going to be the negative version is my guess, but we'll see. E to the 0 power, again, is just 1. So this means that a is negative 6. So this is going to be negative 6 e to the negative 6x. And there is my solution to my differential equation. That satisfies the initial condition given, meaning when x equals 0, y equals negative 6. So in that case, the absolute value gave us the negative version because our initial condition worked out that way. All right, next up, problem 4 on our handout. Starts with dy dt in this case, which is fine. 4y minus 17. In our initial condition is 6, meaning when x equals 0, y equals 6. I'm going to divide through by the y minus 17. And now I've separated my variables. I'm going to integrate. Now you might be asking, could you move the 4 over as well? Yeah, you could. It's not going to matter. Once again, I'm going to convert this into exponential form. And we know e to the c now is just a. And let's figure out what a is based on our initial condition. So when y equals 6, we get that a is e to the 0. That's just 1 again. So a in this case is negative 11. Which means y is negative 11 e to the 4t plus 17. I just added that 17 over. You can add the 17 over earlier if you want, doesn't matter. All right, and we are moving on to number 5, which I'm going to squeeze down here. It's very short. It says let y of t represent your bank account balance in dollars after t years. Suppose you start with $40,000 in the account. In each year, your account earns 8% interest, and you withdraw $8,000. Well, that means we're earning 8% interest. We're taking out $8,000. And that is going to be our first solution. So all they're looking for is just the modeling. They're not looking to solve the differential equation. And part B says, what is the initial condition? The initial condition is $40,000. Meaning that's the amount that we started with in this case. All right, and that brings us to notes. Limited growth. So we are talking limited growth. If a quantity grows at a rate, and so basically, let me kind of summarize what limited growth means. Let's say that you have a really hot product and you spend a whole bunch of money on advertising and you're like, this is the hottest product on the planet. Come check it out. I've got it. Come do it. And you spend a lot of money in advertising, but you get a lot of response. And so a lot of people come and buy your product. So you have what's called limited growth. Because after a little while, all that advertising and stuff, it's going to run out, and enthusiasm for the product is going to run out, so it's going to die down. And that's kind of the idea here. And we can model that with our limited growth model. And we have y prime. Now remember, y prime is the same as dy dt, or dy dx, depending on what we're doing. K is a constant. M is the maximum size of y. Now finding m in real life is a bit complicated, but the good news is they give all that information to us. So let's move to our first example. A manufacturer estimates, I'm going to switch back to my blank sheet. It's going to be a lot easier to do, but I will continue to read the problem for you. A manufacturer estimates that she can sell a maximum of 115,000 cell phones in the city. So there's our M. By advertising heavily, her total sales grow at a rate proportional to the distance. Okay, so that's the model that we have up there. Now we're going to assume that when she first starts, she has sold no products. However, they tell us in the problem that after 3 months, she has sold 50,000 products. And we're going to use this information to build our equation. So our dy dt is equal to k m minus y. And we have some information. So we have that m is the 115. I'm going to go ahead and move things around. This is going to give me 1 over m, which is 115 minus y, dy equals kt. K dt, pardon me. And I'm going to integrate both sides. Now we need to be careful with this integral. On the left side, because of the minus y, I end up with an extra negative ln of 115 minus y equals kt plus c, which means ln of 115 minus y equals negative kt plus c. And I'm going to convert that. E to the negative c is just another constant, so we'll call it a, then e to the negative kt power. All right, I'm going to solve for y by subtracting the 115. And dividing by -1. All right, I'm going to use my first initial condition, meaning y equals 0. I get negative a, e to the 0 power plus 115. This means a equals 115. So we've used the first initial condition to come up with a. Now a is 115, but when I plug back in, notice that equation is negative a, so it's negative 115. And now I'm going to plug in when t equals 3, we get 50. This one there. Now I need to figure out what k is, so I'm going to subtract that 115. So let's do 50 minus 115. And I'm going to divide by negative 115. Let's get a fraction. So I'm going to get e to the negative 3k equals 13 over 23. That's subtracting the 115 divided by the negative 115 in front. And I'm going to convert this into logarithmic form. So this gives me that k is the natural log of 13 over 23 times negative 1/3. Oops, not yk. K. All right. Now that we have k, this is going to get a little tricky. I want to come back to, I want to make it very clear. I'm going back to here. And I'm going to plug in k. Now be careful, and I want to really emphasize this. Negative, those are going to go away. So it's just going to be a positive up there. And we're going to get a little crazy. This is going to become y equals negative 115 e to the ln of 13 over 23 times 1/3 times t from the original problem. So that's t over 3. And I know this is getting a little technical, but this, if you remember, e to the ln reduces out. So we get y equals negative 115, 13 over 23 raised to the t over 3 power. If you're wondering about the negatives, remember they canceled out with the negative k up there and the negative 1/3. And so here is, oops, I'm forgetting the plus 115. So here is our final function as a function of t, with all of our constants filled in, so yay. However, that's not what they're asking for. They want to know if she enters a new market after 3 months, her total, okay, find a formula for the total sales in thousands, which we've done, and estimate the total sales at the end of 1 year. Okay, so here is our first answer here that I've just highlighted. And 1 year is going to be 12 months. You would agree? So y of 12 is going to be negative 115, 13 over 23, 12 divided by 3 plus 115. So let's see what we get. So 13 divided by 23, raised, now 12 divided by 3 is just 4, times negative 115 plus 115. So it looks like we're going to make about 103,263 thousand phones. And that ultimately is what the question is asking for. I mean, they want the equation as well. Ultimately, that's the blank that they give us there that they're looking for. All right. So we're going to move on to logistical growth. Let's clear that out. And we're going to get a fresh sheet for that one. However, I want to go back to our notes, logistical growth. And I want to point out, I wrote on this before, that the blue that's in the yellow up there, and then the blue down below are the same formula. But instead of y, they're using p. Instead of capital M, they are using a capital K. So I translated the, looks kind of pinkish with the yellow, and then the pink down below is the translation. Now I'm going to use our pink. So I'm going to use what they have in the actual problem here to do this problem. And I'm going to go ahead and switch back to my notes, but I just want to kind of point out that they're the same two formulas. One's a differential equation. The other one is the solution. But they used slightly different letters. So hopefully it won't get us too confused. So let's go back to our blank sheet. And here is our logistical growth. I want to point out that y is capital K over 1 plus a e to the negative kt power. That in this particular problem, they give us that at t equals 0. I should say instead of y, they're using, no, we're using y. No, we're using p. They use y. So we're going to use p. And this is a function of t. And at t equals 0, they tell us that there were 500 fish, meaning it says biologists stocked a lake with 500 fish, so there's our initial condition, and estimated the carrying capacity, the maximum population, is 3,900. So we're getting that capital M, or we're using capital K for this problem, is 3,900. And it says the number of fish tripled in the first year. So this means P of 1 is 3 times 150, or 3 times 500, which is 1,500. This is at t equals 1. So we are going to use our two initial conditions here to figure out what a and k are, lowercase k, which is part of the exponent. So let's see, we're starting here. And we're going to start with our initial condition, meaning t equals 0, p equals 500. Now that's a times e to the 0 power because we're plugging in t is 0, and e to the 0 power is just 1. So we're here. And I'm going to cross multiply and divide. I'm going to get 39 over 5. And I'm going to subtract 1. It's going to be 34 over 5. So we have our initial function. We are now here. All right, I'm now going to use the other condition, meaning t equals 1, p of 1 equals 1,500. So this is going to give me 1,500 equals 3,900 over 1 plus 34 over 5. Now, t is equal to 1 in this case, so this is just to the negative k power. And my goal here is to solve for k. So I'm going to, again, cross multiply, divide. So I'm going to get 1 plus 34 over 5 e to the negative k equals 39 over 15. I'm going to subtract a 1. That's going to give me 39 over 15 minus 15 over 15, which is 24 over 15, which reduces to 8 over 5. So I have 34 over 5 e to the negative k equals 8 over 5. I'm multiplied by the reciprocal of 34 over 5. This is going to be e to the negative k equals, the 5's reduce out. I get 8 over 34, which reduces to 4 over 17. Here is my k. I want to get a decimal approximation there, just so we have an idea. So negative natural log of 4 divided by 17. And so this is going to be 1.4469-ish. So this is the first thing that they ask for is k. I prefer the exact form, so I'm going to include it. But your homework may want you to write it as decimal, so it really doesn't matter. Okay, so we are back to y equals, so we're back to our original function, not y, p of t is now 3,900 over 1 plus 34 over 5 e. Now be careful, the k is negative and there's a negative in the formula, so the negatives are gone. This becomes ln of 4 over 17 t. So let's write this here. So p of t is 3,900 over 1 plus 34 over 5, 4 over 17 to the t power. And there is our total function. Sweet. Now, if you wanted to, you could have written with decimals, but I don't like that because then we have to round off, but it's not wrong to do that. They may really want that. This is all part A. So part A. Part B says, how long will it take to increase from to 1,950, half of the carrying capacity? All right, I'm actually going to do part B down here. Put more room. Part B. So it says P of T equals 1950. So I'm going to go to my formula up there. So 1950 equals 3,900 over 1 plus 34 over 5, 4 over 17 to the t power. And once again, I'm going to cross multiply. I'm going to get 1 plus 34 over 5, 4 over 17 to the t power equals now 3,900 divided by 1950 is just 2, which means 34 over 5. So 2 minus 1 is just 1, which means 4 over 17 to the t power equals 5 over 34. Taking the log of both sides, I get t natural log of 4 over 17 equals the natural log of 5 over 24. Let's see what we get. Natural log of 5 divided by 24 divided by the natural log of 4 divided by 17. And I'm getting a slightly different answer than what I got with my notes. Oh, that should be 5 over 34, not 24. Sorry about that. Let's fix that now. So we'll take that here. So we have ln 5 divided by 34 divided by ln 4 divided by 17. There we go. And that matches my notes, 1.3248. And that is in years. So that was a lot of work. I'll grant you that. We only have one more problem to go after this. It's actually a lot easier than these other two that we just did. So this is number 10 on the last page in section 3.8. And it says, a new cell phone is introduced into the market. It predicted that sales will grow logistically. The manufacturer estimates that they can sell a maximum, so here's our maximum, of 100,000 cell phones. After 28,000 cell phones have been sold, the sales are increasing by 8,000 cell phones per month. So here's basically what this is saying. This is saying that at y equals 26, the change of y with respect to time is 8,000 cell phones per month. So if we go to our equation, dy dt, and I'm going back to the original one that was from our notes. From the original notes, so this is going to be ry of 1 minus y over m. And they insist on plugging in eight equals 26 r. 1 minus, now y is 26. M in this case is 100. And we are going to solve for r for this. So 8 equals 26r. This gives me 74 over 100. And let's see what we get. 26 times 74 divided by 100. And so this is going to be 8 equals 481 over 25. R, which means 25 times 8. So this is going to be R equals 200 over 481. So our differential equation is going to look like this. dy dt equals 200 over 481y, 1 minus y over m. And that is what we are looking for. The m in this case is 100 for this particular problem. And that is our differential equation. All right, now a lot of moving parts with this section. You may need to slow down and try each one again. Good luck to you.